this video, we're going to learn how to solve equations involving trigonometric functions. So we've actually looked at some trig equations so far, but they were trig identities specifically. So trig identities are equations that are going to be true for all values of x, or at least all values that are within the domain of the functions involved in the identity. So for instance, if we're talking about tangent, cotangent, cosecant, and secant, there are certain input values for which those functions are undefined. So those values would not actually be valid for the identity. But as long as we're talking about values that are within the domain of the function, then those particular equations are going to be true for any of those values. Now what we're used to seeing when we solve equations is some solutions, not all values represent a possible solution. What we're used to seeing is what we call a conditional equation. So conditional trigonometric equations are true for some values of x, specifically values that meet the conditions set forth by the equation. So the solutions are not going to be all real numbers or all values within the domain of the trig functions. They're going to be whatever combination of values meet the requirements set forth by the equation. So the periodic nature of our trig functions means that equations will typically have solutions that repeat after a set interval. And this is something that you probably haven't encountered yet in terms of your experience in solving equations. Typically when we solve equations, we have a finite number of solutions. But because our trig functions repeat, because they're periodic functions, solutions to the equations are going to repeat as well. So it's going to look similar to what happens with an identity in the sense that an identity is again true for any value within the domain of the functions being used. There will be potentially infinitely many solutions to a trig equation, but they still have to be solutions that meet the requirements based on the structure of the equation. So we're going to focus on solving equations from 2 points of view. So number one, just looking at the solutions from 0 to 2 pi. In other words, within that first rotation, focusing on that first rotation around the unit circle. But we're also going to look for solutions over the whole set of real numbers, which essentially means describing what solutions look like in general using the periodic repeating nature of our trig functions, recognizing the fact that our solutions do repeat based on the fact that our trig functions have values that repeat as we continue from period to period. So let's look at a basic example and let's talk about what we mean by individual solutions versus general solutions over the whole set of real numbers. So we want to solve cosine of x is equal to 1/2, and we want to find the solutions on the interval from 0 to 2 pi, and then also all solutions, in other words, all solutions over the set of real numbers. So cosine of x is equal to 1/2. We want to know what values of x will make this true. Well, one perspective on solving an equation like this is to think of both parts of our equation as representing y. So we're thinking of y as equaling cosine of x and y as equaling 1/2. So if we were to graph the function cosine x, it would look like this. This would be our single period right here from 0 to 2 pi. A graphical way to think of an equation like this is think of the graph of cosine x intersecting the graph of y is equal to 1/2. So that would be the horizontal line that passes through y equals 1/2. So it would look something like that. So solutions for this equation are going to be represented by any location where those two graphs intersect. So if we're just looking at the region from 0 to 2 pi, then you'll notice that these two graphs intersect in two locations. So we have one intersecting point and then another intersecting point there. So whatever x values, specifically whatever radian measures, are associated with those two locations, those will be the solutions to this equation. But notice if you expand this region and look all the way across the number line, we also have other locations where we intersect that graph where those two graphs intersect. And all of those locations represent solutions as well. What we're going to find, though, is that those locations, these two locations from 0 to 2 pi, we can think of those as, in a sense, generating the other solutions. So all of the other solutions, all of the other locations where our two graphs intersect, those represent angles, radian measures, that will be coterminal to our two original solutions. So for instance, if you were to look at this solution, we'll talk about what it is in just a minute, but if you were to look at this particular radian measure, this particular radian measure is going to be coterminal. It's going to be an angle that's coterminal to this one. So this coterminal angle, which is 2 pi radians away, is also going to be a solution. For this particular fundamental solution, this next solution is going to be coterminal. It's going to be 2 pi radians away. So essentially what we're going to find is if we can generate all the solutions from 0 to 2 pi, in this case we have 2 of them, then the remainder of the solutions over the set of real numbers are going to be closely related to these original solutions based on this idea of the fact that cosine, sine, cosecant, and secant repeat after 2 pi radians. Oh no, a similar kind of thing is going to happen with tangent and cotangent, but the period for tangent and cotangent is a little bit different. Those two functions have a period of pi. But we're going to see the same kind of repetitive thing going on with those two functions. We look for what we think of as fundamental solutions from 0 to 2 pi, and then the rest of the solutions are going to be very closely related to those, just based on this idea of our functions and their periodic nature. So what are these two x values? We're looking for the x values associated with those 2 points where they intersect. Well, they're going to be whatever x values we have, whatever radian measures we have on the unit circle, where the cosine of that radian measure is represented by a value of 1/2. Well, what would those be? You might want to look at your unit circle. At this point, you may have the unit circle pretty much memorized, and if you do, then you'll know that that's going to be a radian measure of pi over 3 at this location. And then the other radian measure, where cosine of that radian measure is 1/2, is going to be the radian measure 5 pi over 3. So over the interval from 0 to 2 pi, our solutions in set notation are going to be pi over 3 and 5 pi over 3. Now from these two basic solutions within that first rotation around the unit circle starting from 0, again we can generate all other solutions, ones we encounter in the positive direction as well as ones we encounter in the negative direction. Just recognizing that every solution is related to the ones before it by an additional rotation around the unit circle, either in the positive direction or in the negative direction. So if we want the solution over the whole set of real numbers, essentially what we want to write is a formula for generating the coterminal angles for pi over 3 and 5 pi over 3. So here's how that's going to look. We're going to use set notation again. We're going to use specifically what we call set builder notation, which is a way to write a set of solutions, but rather than writing individual solutions, we're essentially going to write a formula for how all of those individual solutions are generated. So we start by defining our variable. In this case, our variable is x, and then we draw a vertical line. So the way we would read this is all x such that. And then after the vertical line, we're going to write the formulas for x that represent how we would take these original radian measures and generate the coterminal angles that also represent solutions to our equation. So from pi over 3, if we add on a multiple of 2 pi, we're going to rotate around the unit circle. We're going to get to a coterminal angle, and hence we're going to get to another angle that solves this equation. So pi over 3 plus 2n pi is the formula that takes this fundamental solution, adds on additional rotations, or if n is negative, that means rotations in the negative direction, and generates all of those other coterminal angles that also solve our equation. The same thing for 5 pi over 3. So starting at that angle and then adding on additional rotations around the unit circle. And we do need to make a note, what are the conditions for this variable n, which again just represent the number of rotations we've taken to get from our starting angle to another coterminal angle. So specifically, n is an integer. It can be a positive or a negative integer. So it's not a fractional value, it's a whole value, positive or negative. That is going to be our general solution over the set of real numbers. So any value of x that meets these conditions where x is equal to one or the other, I'm going to put my x equals in there, that represents the whole set of solutions. So if we were to make n 0, for instance, well, this goes away, and that just shows that pi over 3 is the solution. Same kind of thing here. If n is 0, 5 pi over 3 is the solution. If we were to allow n to be 1, well, that would take these two fundamental solutions, add on one rotation around the unit circle, and take us to these two solutions. If we were if we were to allow n to be negative 1, that means take these angles and rotate in the negative direction, which would then generate these two solutions to the equation. And as we continue to add or subtract full rotations, we encounter all of those additional solutions just based on how this function repeats. So that's the basic idea, honestly, behind any trig equation. What changes is, of course, the function we may be looking at. If we look at a different function, we have to take into account some functions have different periods than others. And then we'll add in a little bit of complexity as we change the additional features we see in the equation. What happens if our variable is multiplied by a number? What happens if we're adding on a number? What happens if we add in some exponents? We're going to look at all of those different situations. So let's look at another example. We want to solve this equation. 2 tangent x is equal to the square root of 3 minus tangent x. Now, notice in this first equation, we saw a trig function and we only saw it one time. Here we have the same trig function, tangent, but we have two terms that contain a tangent. So just like with any other equation when we solve for x, we want to combine our like terms. So we want to move over any terms involving tangent. Okay, so I'm going to get all my tangents on one side and get all my constants on the other side. So in this case, I'm going to add this tangent and move it over. So we have 2 tangents already. We add another one, and that gives us 3 tangents. So 3 tangent of x is equal to the square root of 3. And then again, we want to isolate our x, so we're going to divide by 3 both sides. So we get tangent of x is equal to the square root of 3 over 3. And so structurally speaking, we basically have the same kind of equation now. We want to know from 0 to 2 pi, on that interval from 0 to 2 pi, what values of x, what radian measures, have an associated tangent value of root 3 over 3. Well, sine, cosine, those are pretty easy to find because we can just look at the x and y coordinates and immediately read off the sine and cosine from our coordinates on the unit circle. But we know we have to generate tangent by looking at a pair of coordinates. So whenever I see a tangent equation, I like to kind of think of it as what would this value look like in terms of sine and cosine. Now when I look at something like this, I know this has been rationalized. We don't see root 3 over 3 just based on looking at x and y on the unit circle. This is a rationalized version of what we would see just using unit circle values. Specifically, it's the rationalized version of 1 over root 3. Well, we also don't just see 1s and root 3s on the unit circle. We see something like a 1/2 and something like a root 3 over 2. So one possibility, in order to have a value for tangent that's root 3 over 3, is that our sine is 1/2 and our cosine is root 3 over 2. Now, this is kind of a subtle thing, but there's also another possibility. We're taking a ratio of two values, and the ratio comes out positive. So either the two values in the ratio are positive, or alternatively, they could both be negative. So another possible way we could generate this value for tangent is by having a sine that's negative 1/2 and a cosine that's negative √3/2. Well, this pair represents one radian measure. This pair represents another radian measure. So then the question is, what radian measures are represented there, where the sine is 1/2 and the cosine is √3/2? Well, this particular pair is associated with the radian measure pi/6. So one solution to our equation is going to be pi/6. This particular pair, where the sine is negative 1/2 and the cosine is negative √3/2, this would occur in the third quadrant, where the radian measure is going to be 7 pi/6. So from 0 to 2 pi, those are going to be our two solutions. Now, over the set of real numbers, we also need to generate other solutions from these two. Now, this is a little bit different than the previous one. We're going to set it up the same way, so all x such that x meets our conditions. But we have to keep in mind, values for tangent repeat not after a full rotation, but after half a rotation, after pi radians. So just as values for tangent start to repeat faster, solutions to the equation will also start to repeat a little bit faster. They'll repeat not after 2 pi radians, but after pi radians. So one portion of the solutions is generated by taking pi/6 and adding on not multiples of 2 pi, but just multiples of pi, multiples of that half rotation. And then we could do the same thing with 7 pi/6. Now, normally I would write that out just like I wrote it out here, but I want you to notice something. If you were to take, for instance, n equals 1, you would take pi/6, add on pi, which we could think of as 6 pi/6, and in so doing, you would actually generate 7 pi/6. Well, if we can take a value of n right here and generate the other fundamental solution over that first rotation from 0 to 2 pi, well, then we can also generate all of the other solutions that would come from this radian measure. So this particular formula alone can actually generate everything that is, number 1, related to pi/6, but also, number 2, related to 7 pi/6. So whereas with the previous problem we had to write both formulas for both of those original solutions, here we don't have to do so, because if we take half a rotation away from pi/6, we get to 7 pi/6, and in the same way we can generate everything related to 7 pi/6. So in this case, we only need the one formula to generate all the different solutions. And again, we like to make the note, n is an integer, so we know what kind of values we're talking about in this formula. So that is going to be our set of all solutions. Let's add in one layer of complexity. Let's change up the structure of the equation just a little bit. So now we're going to look at equations where we have a coefficient on x, where something is multiplied by x. So we're going to use some additional division to solve equations that contain angle multiples or fractions. Now, from a graphing standpoint, what happens if we take something like, for instance, the sine function and take the sine of 2x? What happens if we have a coefficient in front of our x? Well, from a graphing standpoint, this corresponds to a period change on our graph. Changing the period changes how quickly our solutions, our values for our trig function repeat. So if the period becomes smaller, that means all of our values for the trig function are going to repeat faster. If our period becomes larger, that means they're going to repeat more slowly. It's going to take more time, more distance along the x-axis to end up with repeating values for your trig functions. So this is also going to change how we find solutions, or more specifically, the number of solutions we find. So in general, think of the period shrinking. If the period shrinks, because we complete more cycles along our function's graph in the same distance, this will also double, triple, quadruple, etc. the number of solutions we find within that first rotation from 0 to 2 pi. So normally, as we've seen from these past two examples, normally we're going to find 2 solutions within the rotation from 0 to 2 pi. If we change the period, then we change how many cycles we get from 0 to 2 pi. If we complete more cycles from 0 to 2 pi, then we also add on additional solutions within that same distance because the solutions are repeating more quickly. Now we're also going to have to take a slightly different approach to finding the general solution. Here we're going to start with the general solution, and then we're going to look at the solutions from 0 to 2 pi. So we're going to kind of do both at the same time, but we're going to have to be a little bit more careful about focusing on how the solutions are going to repeat, how we're going to generate those additional solutions we get from our periodic functions. Okay, so given this particular equation, 2 times the sine of 2x, and you may want to have parentheses here, minus root 3 is equal to 0. We want to find the general solution, in other words, all solutions over all real numbers, and the solution set on the standard interval from 0 to 2 pi. Now, just like with any other equation, you want to start by isolating x as much as you can, which here means isolate your trig function. So we need to move our root 3, so that's going to be 2 times the sine of 2x is equal to the square root of 3. We need to divide out the 2 in front of sine, so sine of 2x is equal to root 3 over 2, and then we need to pause. Now, you cannot divide out the 2 inside the sine. That would be like taking something with a square root with 2x under the square root and then trying to divide that out. It doesn't work. It's inside the function, and so we have to think of this sine of 2x as the function as a whole. Now, for just a moment, I want to forget that there's a 2x here. It's just the sine of a number is equal to root 3 over 2. Well, if the sine of a number is equal to root 3 over 2, what would be the associated radian measures associated with the sine value between 0 and 2 pi? What would they have to be? Well, the 2 radian measures between 0 and 2 pi, where the sine has a value of root 3 over 2, are going to be pi over 3, and then also 2 pi over 3. So based on that, I know that this number, whatever this number happens to be, it either is going to be pi over 3 or it's going to be 2 pi over 3. Now, we can't forget though, this is not an x under here, it's a 2x. But 2x, our input for sine, has to either have a value of pi over 3, so that its sine is root 3 over 2, or 2 pi over 3, so that its sine is root 3 over 2. So from this, I generate my 2 general solutions, not just focusing on pi over 3 and 2 pi over 3, but the general solution associated with those. And I'll show you in just a moment why we have to go general before we can go specific. So we know that 2x, the input for our trig function, is going to be, in general, pi over 3 plus or minus some additional rotations. And again, we know it's going to be full rotations because we're talking about sine. Sine has a period of 2 pi. Or possibly, our input for our trig function is going to be 2 pi over 3, or coterminal angles to 2 pi over 3. Now, we're not quite done. Why are we not quite done? Well, x has not actually been isolated. So we interpreted what the trig function is telling us, but we haven't actually solved for x, because notice both of these equations we now have, both of these formulas are in terms of 2x. So we're going to have to divide out that 2 in both equations. Now here's where things start to change, and they change again because of this new structure and because of what that means in terms of the period change. So when I divide out 2, I have to divide 2 from all 3 parts of the equation, including the part where I was generating those additional rotations, those coterminal angles. I'm going to have to do it for all 3 parts in both equations. Now that's going to isolate x, but it's going to change what we see on the other side of the equation. So simplifying all of this down, our general solution is all x such that x fits into this formula or it fits into this formula. So for the first one, it's going to be x is equal to pi over 3 divided by 2. Well, if we're doing something like that, that 2 can essentially just go to the denominator. So pi over 3 divided by 2 is the same thing as pi over 6. But notice when we divide by 2 over here, we no longer have 2 in pi. In other words, multiple rotations around the unit circle. These 2's are going to cancel as well. And so we're only left with in pi. That means half rotations. Why did this happen? Well, the period change here means we're repeating solutions faster. In this case, we're repeating solutions after half a rotation, not after a full rotation. That's the effect of having the 2 there. It makes the solutions repeat in half of the amount of time. We get twice the number of solutions in the same amount of time across the same distance. And then we have to do the same thing over here. So if I were to move my 2 up here, that becomes 2 pi over 6, which reduces to pi over 3. And again, same thing with that rotational component. Now our solutions don't repeat after full rotations. They only need a half rotation to repeat. And again, n is an integer. Now here is why we have to generate the general forms first. What are the solutions going to be between 0 and 2 pi? Well, pi over 6 and pi over 3, those fundamental solutions we got just from solving, isolating x, those will be solutions because those are between 0 and 2 pi. So one solution is going to be pi over 6, one solution is going to be pi over 3. Now what if we use these formulas and add on half a rotation? In other words, what if we allow n to be 1? Well, if we were to take pi over 6 and add on a single pi, pi over 6 plus pi, we could think of that as pi over 6 plus 6 pi over 6, otherwise known as 7 pi over 6. So 7 pi over 6, which is generated from this formula, is another solution to the equation. And notice, it's also within that rotation from 0 to 2 pi. So it is also included as a solution with the 2 fundamental ones we found. Now, same thing if we let n be 1 here. If we take pi over 3 and add on half a rotation. If we were to think of this as 3 pi over 3, then pi over 3 plus 3 pi over 3 is going to give us 4 pi over 3, which is, again, also within that range from 0 to 2 pi. So it also is included as a solution. If we were to go further, add on another half rotation, well, that's going to take us out of this interval. So these are going to be the solutions we get over that interval. And notice what happened. With the 2 examples on the first page, we took an equation something like this and we generated 2 solutions across our interval from 0 to 2 pi. Well, here we have not only 2 solutions, we have 4. We doubled that. Having this 2 here ended up doubling the number of solutions we could get from 0 to 2 pi. So that's the effect we're going to see based on how this changes. We get double the number of solutions within that first rotation. But the reason we have to do the general solution first is because finding the general solution is going to tell us how this rotational component changes, how that component that generates those additional solutions is going to change. So we're still going to find the same fundamental solutions when we divide out 2 and isolate x, but the other solutions that we would get, we only get once we generate the correct rotational component, dividing out that 2 from all parts in the equation. Now this is a little bit different, so let's do another problem like this. Okay, so our equation is 5 plus the cosine of 3x is equal to 4. And again, we want to find the general solution to this equation, the formula, and the solution set within our first rotation from 0 to 2 pi. So again, start by isolating your trig function so that we can isolate x. So I need to subtract 5 and move it over. So cosine of, and I'm going to put it in parentheses, cosine of 3x is equal to 4 minus 5, which is negative 1. So we have our trig function isolated. Now we can think in terms of the unit circle and think about what we're looking at here. Now this is a little bit different than something like saying the sine of a number is equal to root 3 over 2. We know there's 2 locations on the unit circle where we get a sine value of root 3 over 2, at least within that first rotation. But for this one, now we're saying the cosine of our angle is negative 1. In other words, we're looking at a radian measure where the x value, the cosine's value, is negative 1. Well, if we're looking within that first rotation, that only occurs in one location. That's only associated with one radian measure. So a cosine value of negative 1 is associated with a radian measure of pi radians. So that means our angle, the argument for cosine, in order for cosine to be negative 1, the value within the cosine has to be equal to pi. So that means our input, 3x, is equal to pi, or in general, pi plus our additional full rotations. Again, cosine has a period of 2 pi. It repeats after full rotations. So plus 2n pi, plus those full additional rotations in the positive or negative direction. Now here we only get the one formula because there's only one value that would satisfy this equation that's within the range from 0 to 2 pi. So that only generates one portion of formula, whereas previously we had more than one. Okay, so now we need to determine what needs to happen for x. So divide your 3 from all 3 parts. That's going to isolate our x, and it's going to change not only the solution we get that's on 0 to 2 pi, but it also changes our rotational component, and that's going to give us the general solution. So it's going to be all x such that x is equal to pi over 3 plus 2/3 pi. That's going to be the single amount of rotation, multiples of 2/3 pi. So 2n pi over 3, again where n is an integer. What does that mean for our solutions for 0 to 2 pi? Well, let's think about what happened for the previous one. For the previous one, we set our equation up, we isolated the trig value, and we recognized there's 2 values on the unit circle associated with a sine of root 3 over 2. So we started out with 2 solutions, and then isolating x put us in a position where we could actually generate 4 solutions. So we generated double the number of solutions we would have otherwise found. Now here we have a 3x inside of our trig function. Now forgetting about the 3x, we only generated one solution. We generated a solution of pi. But what's going to happen when we use the formula to find our additional values? Well, just like having a 2 doubled the number of solutions we got, having a 3 is going to triple the number of solutions we get. Now, that does not mean we're going to get 6 solutions. It means we're going to get triple the number of solutions we originally found. And we originally found only 1. So we should expect to find triple that, which would be 3. So let's generate those solutions. So pi over 3 is going to be one of them. and then the other ones will come from adding on multiples of 2 pi over 3. So if we were to add on a single multiple of 2 pi over 3, that's going to give us pi over 3 plus 2 pi over 3, which is 3 pi over 3, which simplifies down to pi. So that's going to be another solution. Well, what if we kept rotating? So what if we went from pi and then added on an additional 2 pi over 3? Well, again, think of pi as 3 pi over 3. So 3 pi over 3 plus 2 pi over 3 is going to give us 5 pi over 3. If we were to add on another, we end up at 7 pi over 3, which is outside of this range. So those are going to be our 3 solutions. And again, we got triple the number we would have otherwise gotten just focusing on the values we get from cosine on the unit circle. So this is what happens when we have a coefficient in front of x that's going to be greater than 1. Coefficient in front of x changes the period. We take the original period, which in this case was 2 pi, and divide it by these numbers, which means we repeat our solutions more quickly, which means we get more solutions within the same distance from 0 to 2 pi. What happens if the coefficient in front of x is less than 1? In other words, what happens if we have a fractional coefficient? Something very similar happens, and we approach the problem in the same way. So let's solve this equation. So -1 plus the sine of x over 2 is equal to 0. And again, we want to find the general solution and then the solution set from 0 to 2 pi. So start by isolating your trig function. So sine of x over 2, I'm going to put that in parentheses, add your 1, so that's going to be equal to 1. So sine of some value is equal to 1. What values from 0 to 2 pi are associated with a sine value of 1? Well, that's going to be a radian measure where our associated y-coordinate is equal to 1, and that only occurs at pi over 2. So that means x over 2 is equal to pi over 2, and then we're talking about our sine, which repeats after 2 pi radians, so plus multiples of 2 pi. Now we're in a similar situation as we were with the last 2 examples, but now we don't have to divide out to isolate x, we actually have to multiply to isolate x, and we have to do the same thing on both sides of the equation. So I'm going to multiply in order to isolate my x. This 2 is going to have to distribute to both terms in parentheses. So that's going to give us our general solution. So all x such that x is equal to, well, pi over 2 times 2, you can think of this as 2 over 1 if that helps. The 2's are going to cancel, and so pi over 2 is just going to become pi. And then when we multiply our 2 by that rotational component, that's going to be 4n pi, which means a double rotation. If 2 pi is 1 full rotation around the unit circle, 4 pi radians is 2 full rotations. And again, n is an integer, any integer. So what does it mean for the graph of sine if we have a coefficient of 1/2 in front of x? It means that we're doubling the period. It means we're making the period longer. We're going from a period of 2 pi to a period of 4 pi. It means it takes double the distance for our values to start repeating. So when we look at our solutions, our fundamental solution from 0 to 2 pi is going to be included. But we wouldn't get to another solution until we add on an additional 4 pi, which would take us to pi plus 4 pi, which would be 5 pi, which is way out of this interval. So in this case, we only get one solution, just the solution pi. So kind of different in the terms of the effect that the coefficient had in this case. We still get that one fundamental solution, but we don't generate any additional ones from that. So we only have that one on that interval from 0 to 2 pi. So there's a few examples of what's going to happen when we have a coefficient in front of x, And again, that corresponds to a change in the period, which changes how quickly our values repeat, and as such, how many solutions we're going to get from 0 to 2 pi. Now, there's another possible situation we could run into. What happens if we have addition or subtraction inside of our trig function? Well, that corresponds to a phase shift. So when a phase shift is present, there is a corresponding shift in the location of fundamental solutions. In other words, those basic solutions from 0 to 2 pi. Now, this is not going to change the rotational portion. If we're just taking x and adding on a number, not multiplying or dividing by a number, but just adding on something, that does not change the period. It does not change how far, how quickly it takes to repeat our function's values. It just shifts the graph. It shifts those original locations for those original solutions. Now, the only thing we have to be careful about in this case is we have to account for the possibility that when we shifted, some of our solutions will shift out of that standard interval from 0 to 2 pi. So we have to be very mindful of the effect that this shift is going to have on the graph. Some of the solutions we generate will shift far out of the original range that we want, from 0 to 2 pi. Some may shift into the range that otherwise would not be within that range. So we have to be very mindful when we're generating solutions to keep in mind that we're only looking between 0 and 2 pi radians. So let's try this one. We have the sine of x minus pi over 3, and that's equal to negative root 2 over 2. And again, we want to find the general solution and then the specific solutions from 0 to 2 pi. Well, here our trig function is already isolated. Now, what can we not do? We cannot add pi over 3. It's inside the trig function. Again, think of it like being under a square root. You can't just add something that's under a square root and move it over. It doesn't work that way. So now we think in terms of the unit circle. The sine of our input gives us a value of negative root 2 over 2. So what radian measures would be associated with a sine value of negative root 2 over 2? In other words, what radian measures are associated with a y value of negative root 2 over 2? Well, negative y's are going to occur in quadrants 3 and 4. And those specific values are going to be 5 pi over 4 and 7 pi over 4. So our angle in question, the input in question, x minus pi over 3, is going to be equal to either 5 pi over 4 plus our potential rotations. And again, we haven't changed the period here. It's still the sine function, which has a period of 2 pi. Okay? Or, again, another radian measure that would give us a sine of negative root 2 over 2 for our input would also be 7 pi over 4. Again, plus 2n pi. Now, as with the previous problems, x is not isolated. So we're trying to solve for x, we're trying to isolate x, we still need to do that. That means we need to add this negative pi over 3 and move it to the other side. Now this is a combining like terms kind of thing. Notice these two terms now have a variable. So they are not considered to be like terms with that pi over 3 that we want to move. However, 5 pi over 4 and 7 pi over 4, those are just constants. So those are going to be the terms that we combine with the pi over 3. So I'm going to add pi over 3 to both sides and again combine it with the correct term. It doesn't combine with both, it combines with the like term. And I have to do it on both equations, both formulas. Okay, now you probably need to get a common denominator here. You probably can't do that one in your head. So I would just go out to the side and work out that little problem. So 5 pi over 4 plus pi over 3. We need our common denominator. Well, if we have denominators of 4 and 3, our common denominator is going to be 12. So this fraction needs to be multiplied by 3 over 3. So that's going to be 15 pi over 12. And if we wanted 12 here, we need to multiply by 4 over 4. So 4 pi over 12. Combining together, that's going to be 19 pi over 12. So by doing this, our x is isolated, and then we have a rotational component to continue to rotate from there. Now before we write the general solution, let's go ahead and do the same thing over here. So 7 pi over 4 plus pi over 3. Again, same common denominator, 12. So multiply by 3 over 3 here. So that'll be 21 pi over 12 plus 4 over 4 times pi over 3, which is going to be 4 pi over 12. And that's going to be equal to 25 pi over 12. Now I want you to look at these two numbers that we generated, 19 pi over 12 and 25 pi over 12. Those are going to be solutions to this equation. They will satisfy this equation. So 19 pi over 12, what does that really mean? Well, what is 19 over 12? Let's look at that. So 19 over 12, that is going to be 1.6 roughly. So we're talking about roughly 1.6 pi. Okay, well 1.6 pi is between 0 pi's and 2 pi's. So this will be within the correct range for purposes of writing our actual individual solutions. But what about 25 pi over 12? Well, if we were to take 25 and divide it by 12, we get about 2.1. In other words, about 2.1 pi. Well, we only want solutions from 0 to 2 pi, and this is approximately 2.1 pi. So it is actually out of the range in which we want to consider values. It's outside of that interval. So this will not be one of the solutions from 0 to 2 pi. It's too far out. And the reason it's too far out is because of what this represents. By subtracting inside of the trig function, that would take the original graph and shift it to the right. So this original solution got shifted to the right so far that it left that interval from 0 to 2 pi. So how do we deal with this problem? Well, we can take this number, this radian measure, that's outside of our interval, and we can generate something that's coterminal that is inside of our interval. So what would the coterminal angle be? Well, if we were to take 25 pi over 12, the coterminal angle, if we rotated backwards, would require us to subtract 2 pi from it. Think of this as 24 pi over 12. That's equivalent to 2 pi. So 25 pi over 12 minus 24 pi over 12 would give us just a single pi over 12. This would be the corresponding solution that's within that particular interval from 0 to 2 pi. So even though the shift took our fundamental solution and pushed it out of the interval, we can always generate a coterminal value, and it also solves our equation and represents what we want that is between 0 and 2 pi. So I'm going to use these two values to write our general solution. Now again, just as a reminder, notice that rotational portion, that did not change. Shifting does not change the period of the function. It just shifts the period to the left and the right. It means we're looking at something that's either to the left of where it normally is, or in this case, something that's to the right of where it normally is. But things are still repeating after 2 pi radians, so that has not changed. What's changed is just these fundamental solutions. So all x such that x is equal to 19 pi over 12, or let's start with the smaller one. It's equal to pi over 12 plus our rotations. Now if we were to let this be 1, that would be pi over 12 plus 24 pi over 12, and we generate 25 pi over 12. So we'll generate this solution from this formula. Or potentially, we're equal to 19 pi over 12 plus 2n pi. And again, n is an integer. So that is our general solution. And based on that, our solutions from 0 to 2 pi are pi over 12 and 19 pi over 12. Why do we not have additional solutions like we did with the previous examples? Well, again, the period hasn't changed. The number of solutions we see within that interval from 0 to 2 pi has not changed. We've shifted our solutions. We haven't changed the number of the solutions because the period is still the same. We still repeat the same way as we normally do. So that's another type of situation we can run into. Now, let's take it one step further. Not focusing so much on what's inside of a trig function, but let's look at cases where we either have exponents on our functions or possibly different trig functions within the same equation. So maybe a sine and cosine within the same equation. Typically, we end up having to do some type of factoring. Exponents, solving equations with exponents, typically we end up factoring something. Different trig functions will end up factoring something with a GCF in most cases. So when we do equations like this that either have an exponent or have more than one trig function, different trig functions in the same equation, we want to start by getting all terms, including ones that don't have the trig function, including ones that are just constant terms, get all terms to one side of the equation and get a 0 on the other side. You're then going to factor what results and then set each factor equal to 0. Now, one thing we have to be mindful of, particularly from the standpoint of having different trig functions in the same equation, it is possible to end up with an equation that is extraneous. It can't be solved, or potentially the solution we generate works in one of our trig functions, but it's undefined in our other trig functions. So for instance, when we have tangent, cotangent, cosecant, and secant, remember those four functions are not defined for every x value. So it's possible we generate a solution that wouldn't work in one of those particular situations. So big takeaway is whenever we're looking at an equation that has exponents or different functions, you have to check your solutions. Check your solutions. And again, especially in that case where we have the different trig functions present in the same equation. Okay, so let's try an example. So we want to solve the equation 2 times the sine squared of x plus 7 times sine x is equal to 4. And once we introduce exponents, once we introduce different trig functions to the same equation, we're just going to focus on finding the fundamental solutions. How periodicity works once we have these slightly more complicated equations, sometimes it's not going to work the way we really need it to, so we're just going to focus on those fundamental solutions within that first rotation around the unit circle. So I see an exponent. This means take sine and square it, okay? So I need to get everything on one side since I see that exponent. So that means I need to subtract my 4 and move it over. So 2 times the sine squared of x plus 7 times the sine of x minus 4 is equal to 0. Now we need to factor this. Now you may see this and see these signs and think, what am I supposed to do in this situation? This is a really complicated problem. So here's a strategy to use if you see something like this and it looks like it's going to be a major challenge to factor. We're going to do what's called a substitution. So in place of the trig function sine x, we're just going to temporarily substitute a variable. So I'm going to use the variable u, and I'm going to allow u to be equal to the sine of x. This is only going to be a temporary substitution, but essentially what's going to happen is wherever I see a sine x in my equation, I can substitute this variable u. I'm changing what the equation looks like, but I'm not fundamentally changing its form, at least from the standpoint of being able to factor. So I'm going to temporarily substitute a u in place of sine x. So that's going to be 2 times u squared plus 7 times u minus 4 is equal to 0. So I can factor it in this form, which is the kind of form we're used to seeing, and then once it's factored, I can go back and I can plug in sine x, and I won't have changed anything. So go through, pause the video. If you need a minute, pause the video, factor this. If you need to review factoring, now's a good time to review it. This is going to factor as 2u minus 1 times u plus 4. And again, all of that is equal to 0. So I would go ahead and solve for u in this case. We're going to get that u is equal to 1/2 if we set this first factor equal to 0. And we're going to get that u is equal to -4 if we set the second factor equal to 0. Now, that does not mean that our solutions to our equation are 1/2 and -4. There aren't any u's in the original problem. There's sine of x. So now we need to resubstitute, reverse the substitution that we originally did, and then we can solve for our actual variable x. So for the first equation, we have sine of x is equal to 1/2, and then for the second equation, we have sine of x is equal to -4. So within the interval from 0 to 2 pi, what values of x give me a sine of 1/2? In other words, the y-coordinate at these radian measures is 1/2. Well, that's going to be pi over 6 and 5 pi over 6. What about this one? Well, remember sine and cosine, we've defined those in terms of the unit circle. Coordinates on the unit circle, the x and y coordinates. Well, the y value corresponds to sine. We know the highest y value on the unit circle is going to be +1, and the lowest y value is going to be -1. So we don't actually see a y coordinate of -4 on the unit circle. It's outside of the circle. So this equation is actually extraneous. It doesn't necessarily mean you made a mistake. It just means this is an equation that results from the original one that doesn't actually have a solution. So the solutions to this problem only come from this first equation, from this first factor. So we end up having these two solutions in this case. Let's try another one similar to this, where we have an exponent. So we want to solve the equation cotangent squared of x minus 3 is equal to 0 on our interval from 0 to 2 pi. Okay, so here this is a little bit different. Okay, so we only have one instance of our trig function, only one instance of the variable. So when that is the case, we can actually just isolate the trig function. And that's a general rule with pretty much any equation. We can use what's called the square root property. So if you can isolate whatever is being squared, you can take the square root of both sides of the equation. And that's going to be a lot easier in this case. So if we move our 3 over, we have cotangent squared of x is equal to +3. And then we can take the square root of both sides. The one thing we have to remember is that when we take the square root, we need plus minus on one side of the equation. So we need plus minus on that side of the equation. So I'm looking for values of x, radian measures, between 0 and 2 pi that correspond to a cotangent value of the square root of 3. Now, just like with tangent, we looked at a tangent on the first page. Cotangent is a little bit more complicated to find on the unit circle because it involves combining the two coordinates at whatever radian measure you're looking at. So how would we generate a square root of 3 or a negative square root of 3 from our x and y coordinates on the unit circle? Well, just like with the tangent, it's helpful to think of where that root 3 would have come from. So I'm going to rewrite root 3 in a slightly different way. I know that my cotangent and my tangent are always defined in terms of a ratio. It's the ratio in this case for cotangent of cosine over sine. So root 3, if I want to write it immediately as a ratio, I can write it as root 3 over 1. Well, I don't see just a root 3 or just a 1 on the unit circle. I see root 3 over 2 and 1 over 2. But because we're looking at situations where our cotangent could be positive or it could be negative, we want to consider situations where each of these values is positive or negative. So since it's cotangent, we're looking at a cosine of positive or negative root 3 over 2, and we're looking at a sine of positive or negative 1/2. So what values of x, what radian measures between 0 and 2 pi, would correspond to these x values and these y values? Well, in the first quadrant, pi over 6 is going to have a cosine of root 3 over 2 and a sine of 1/2. In the second quadrant, 5 pi over 6 is going to have a cosine of negative root 3 over 2 and a sine of positive 1/2. In the third quadrant, 7 pi over 6 is going to have a negative and negative, root 3 over 2 and 1/2. And in the fourth quadrant, 11 pi over 6, the cosine is positive, the sine is negative. So those are going to be our 4 solutions. This is similar to the issue with having a function where the period changes in terms of what happens to the number of solutions. Once we have that square, squaring changes the number of solutions we expect to get. If we just had the cotangent is equal to root 3 or negative root 3, there will be 2 solutions on the unit circle corresponding to that particular value for cotangent within our interval. Once we square, we open up the possibility of a positive or a negative value for our trig function, and that's going to double the number of solutions we find. Okay, let's look at an example where we have a different trig function involved, not just one type of trig function, but a different trig function involved in our equation. So here we have tangent and we have sine in the same equation. So tangent x times the sine squared of x is equal to tangent x, and again we want to solve on that interval from 0 to 2 pi. Now here's something that's very tempting to do that you cannot do. You see that tangent on both sides and you think, okay, I'm going to divide that out. It's common, I can divide it out. Yes, you can, but by doing that, you eliminate any of the solutions to the equation that come from the tangent function. Dividing and eliminating the tangent divides and eliminates one instance of the variable, which means you lose solutions to the equation. So dividing out that common tangent on both sides is not an option here. So this is a situation where you get everything on one side and you factor. So we need to subtract the tangent x and move it over. So we have tangent x, sine squared x, and we're going to subtract the additional tangent x to move it over. Now keep in mind these are not like terms, they don't combine, they truly are separate. Now we're looking for a greatest common factor, something these terms have in common, and it's that tangent x. So now we can divide it out, but we're dividing it out in the form of factorization so that it's not eliminated from the equation, it's factored out of the equation. And so we're left with sine squared of x minus 1, and that's equal to 0. So now I can set each of these equal to 0. So tangent of x is equal to 0, and then sine squared x minus 1 is equal to 0. And I solve each of these independently. So if tangent is equal to 0, that means the sine was 0, and then the cosine was not 0. So those would be radian measures of 0 and pi. Those are the 2 locations where our sine has a value of 0, and then at 0 radians our cosine is 1, at pi radians our cosine is negative 1. We take the ratio for tangent and we get a 0. Now here we need to isolate our sine, so add the 1 to both sides. So sine squared of x is equal to 1. Take the square root. Don't forget your plus minus when we take the square root on the numeric side. Square root of 1, but plus or minus square root of 1, which is 1. So what values of x correspond to a sine of positive or negative 1? Well, a sine of positive 1 between 0 and 2 pi occurs at pi over 2 radians, and a sine of negative 1 occurs at 3 pi over 2 radians. Now, as I mentioned on the previous page, we have to check our work, particularly in these situations where we have two different trig functions present in the equation, specifically a trig function that doesn't have a domain of all real numbers. So sine, you can plug in any value you want and you're not going to have a problem. So if we plug in 0, it's okay. If we plug in pi, it's okay. This function is still defined. But tangent does not have a domain of all real numbers. Tangent is undefined for certain radian measures. So we need to double check that these two solutions that were generated from the sine function, we need to make sure that these are okay for tangent. Well, what happens if you plug in tangent of pi over 2? So it may help to visualize this in terms of what this looks like. So here's pi over 2. And there at pi over 2, we know the ordered pair is going to be 0, 1. And then here at 3 pi over 2, the ordered pair is going to be 0, negative 1. What can we say about the value for tangent at these two radian measures? Well, it's going to be the sine, which is our y, divided by the cosine, which is our x. So at pi over 2, sine over cosine, aka tangent, is 1 over 0, which happens to be undefined. At 3 pi over 2, tangent, which is sine over cosine, is negative 1 over 0, which also happens to be undefined. So although these two solutions satisfy the sine portion of this equation, they are not included in the domain of the tangent function. So if we were to plug them into the tangent function, they give us something that is now undefined. So these are not actually solutions to the equation. Now what about 0 and pi? Well, they came from the tangent, so we know they're okay with tangent. And again, sine has a domain of all real numbers. We can sub in any radian measure we want, and the sine will be defined. So 0 and pi are going to be solutions to our equation. Okay, let's look at one other situation where we have two different trig functions, but maybe we have to take a slightly different approach. So what happens when we have an equation that maybe has exponents, maybe has more than one trig function, but it can't be factored the way we factored the previous one? If that's the case, it's possible that identities may be used. If we can use an identity that gets rid of one of our functions and writes it in terms of the other function, then we can go from there and we may end up with an equation that we can solve. So we want to solve the equation secant squared of x minus tangent of x is equal to 1 on our interval from 0 to 2 pi. Well, secant and tangent don't have anything in common. I could move my 1 over, nothing happens. There's no greatest common factor here, so I'm kind of at a standstill. There's not really anything that can be factored here. However, I know that tangent and secant have a specific relationship via that Pythagorean identity that relates tangent and secant. So I want to sub in for secant squared. Okay, I don't have an identity directly relating tangent to secant squared, but I can relate secant squared to a tangent squared, which will then take this equation and put it entirely in terms of that one function, tangent. So what would I sub in? Well, based on that identity, based on the Pythagorean identity, we know that secant squared of x is the same thing as tangent squared of x plus 1. And so I'm going to sub that in to the equation. And now I have an equation that's entirely in terms of that one trig function, and it's going to be simpler to solve. Now, as I solve, I'm going to be solving in terms of tangent, but I have to keep in mind the original equation not only had a tangent, but it also had a secant. So this issue with having a function where certain values may make that function invalid, may make it undefined, that also will have to be considered with an equation like this. Something may work for tangent, but it may not work for secant, so we need to double check once we get to the very end of the problem. Now, I have two instances of my trig function, one with an exponent, one without, so that's a good indication that I need to get everything on one side of the equation and factor. So 1 over here on the right can be moved over with subtraction. Notice we also have a positive 1 over here, and that's what we would combine it with. So if we subtract it and move it over, this one is just eliminated. So we're left with tangent squared x minus tangent x is equal to 0. And so now I can factor. It's the same thing, but think of it again in terms of a greatest common factor. What do these two terms have in common? Well, this term has two tangents, this term has one, so I can factor out that single common tangent. So from the first term, that's going to leave me with tangent x, and from the second term, tangent factored out of tangent just leaves me with a 1. Okay, so now that I have my two separate factors, I can split them up and set them equal to 0. So I get tangent x is equal to 0, and then tangent x minus 1 is equal to 0. So where does the tangent take on a value of 0? So those are going to be locations where my sine is 0 and my cosine is non-zero. And we actually looked at this one above, and we determined that occurs at 0 radians and pi radians if we're looking within that interval from 0 to 2 pi. So here we have solutions of 0 and pi. Now for this equation, I'm not quite there. I need to add 1, move that over. So tangent of x is equal to positive 1. Where does the tangent have a value of 1? Well, if the tangent has a value of 1, that means the sine divided by the cosine was equal to 1, which means the sine and the cosine had to be the same. So I'm looking for radian measures within the interval from 0 to 2 pi where the sine and the cosine would have the same value. Well, in the first quadrant, the sine and cosine have the same value at pi over 4. They both have a value of root 2 over 2. So I divide those two values, I get a 1 for my tangent. We also have a situation there in the third quadrant. Notice in the third quadrant, both of our values will be negative, but if we divide a negative by another negative, the result is a positive. So the radian measure where the tangent would be 1 in that quadrant would be 5 pi over 4. And so those are going to be our two values. We need to check all of these values in terms of our secant, though. We have to go back to the original equation and verify that none of these radian measures violate those two trig functions in the original equation. Well, we know they're okay from tangents point of view because they came from a tangent. We have to check in terms of secant, though. Is secant defined at each of these locations? Well, they're at 0 and pi. Again, let's draw a little coordinate plane. Here's 0, here's pi. At 0, our coordinates are 1, 0. At pi, our coordinates are -1, 0. So what can we say about the secant at those two locations? Well, remember the secant is the reciprocal of cosine. So at 0 radians, our cosine is 1. If we take its reciprocal, it's still just 1, and so the secant is defined there. The cosine is 1 and the secant will also be 1. Now at pi, the cosine has a value of -1, so the secant is its reciprocal, which is also going to be -1. So secant is perfectly fine there. We don't have to worry so much about these two radian measures, just because the only issues with domain occur on our axes, where one of our coordinates is 0. Since all of our trig functions, other than sine and cosine, are defined in terms of ratios, as long as we're talking about values that are non-zero, there's no risk of dividing and ending up dividing by 0. So these two values are automatically going to be okay. So this set combined together, let's write the whole set, that's going to be our solution set. So smallest to largest, that's going to be 0, pi over 4, pi, and 5 pi over 4. That is our solution set. let's look at one final situation that we may encounter with our trig equations. Now, everything we've seen so far has been something that could be solved with the use of the unit circle. What we know about finding our trig values from the unit circle. We know our x always corresponds to our cosine, our y always corresponds to our sine. We can find any of the other four ratios using what we know about sine and cosine. But all of the equations we've looked at so far have been related to unit circle values. 0, 1, root 3 over 2, 1/2, things that are related to those numbers. What happens when we have an equation where we can't relate our trig function to values that we can identify on the unit circle? In other words, our solutions are not going to be special angles, what we think of as special angles, those angles that we label on the unit circle. What happens when our solutions aren't special angles? In other words, multiples of pi over 6 or pi over 4. What happens when our equation involves numbers that don't match up with one of these radian measures or something that's generated from them? If that's the case and we want to solve our trig equation, that's when we're going to use our inverse trig functions. And this is closer to what we do with a normal equation, a non-trigonometric equation. We use inverses in most cases when we solve an equation. We've used inverses already. We just don't necessarily think about it that way. Anytime we want to have an addition and we want to move it to one side of the equation from the other, we do a subtraction because subtraction is the inverse of addition. If we have a multiplication and we want to get rid of it, we do a division because multiplication and division are inverse operations. Well, if we're talking about a trig function and we want to get rid of it, we want to undo a trig function, an inverse function is what undoes a trig function. So anytime we have a trig equation where we can't identify solutions just based on the numbers we can identify from the unit circle, that's when we're going to use our inverse trig functions. Now, there are limitations to using these functions. When we can just identify things from the unit circle, we have nice, pretty radian measure answers, pi over 6, pi over 4, multiples of those two values. As soon as we have to use an inverse trig function, automatically we're going to start running into things that can't be written in terms of pi, that are just going to have to be written in terms of our inverse trig functions, or alternatively evaluated using our graphing calculator. So the answers aren't going to look as pretty, but they are still going to be answers to our equations. Okay, so we want to solve tangent of x is equal to 3 on the interval from 0 to 2 pi. So we want the exact solution or solutions in radians, and then we want to do approximations of our solutions in degrees. So tangent of x is equal to 3. I'm going to write down our equation. Now, I know if I look at the unit circle, I have locations where tangent would be equal to the square root of 3, or maybe the square root of 3 over 3. But I can't readily identify any location on the unit circle where I take the ratio of sine and cosine and end up with a value of 3. So this equation falls under that situation where we're not going to find a special angle, something that's a multiple of pi over 6 or pi over 4, that solves this equation. So our only option to isolate x is going to be to get rid of our tangent function using its inverse. So in order to get rid of tangent, I have to use the inverse tangent. So just like if I were to say, for instance, want to get rid of a square, I would take the square root of both sides of the equation. If I want to get rid of a tangent, I'm going to apply the tangent inverse function to both sides of the equation. And as long as I do the same thing on both sides, I keep the equation in balance. Now on the left-hand side, the general idea is we wanted to eliminate the tangent, and tangent inverse combined with tangent, one applied to the other, they are inverses, and so we're just left with x. The tangent is eliminated. X is equal to what? Well, x is equal to the inverse tangent of 3, whatever that happens to be. Now, if you'll remember, we solved a tangent equation on the first page and we ended up with two solutions. This is only one solution. So what's the other solution going to be? Well, it's going to be helpful to remember what tangent inverse means, or more specifically, what kind of angle the inverse tangent of 3 is going to correspond to. Well, we know when we take an inverse tangent, we're treating this as the value for tangent, and we're asking the question, what angle gives us a value of 3 for its tangent? But specifically, what angle from negative pi over 2 radians to pi over 2 radians gives us a tangent of 3? Well, we may not know exactly what the angle is, but automatically, based on the fact that we're limited to angles that are either in the fourth quadrant or in the first quadrant, since our tangent is going to have a positive value, we know the angle we want is going to be something in the first quadrant. So whatever that angle happens to be, it almost looks like I drew 45. It doesn't have to be 45 degrees. It's just in the first quadrant. Whatever this angle is, that's going to be the inverse tangent of 3. That's going to be one of the solutions to our equation. Now, where else would we get a value for tangent that's positive? There's another quadrant where tangent is going to have positive values. It's going to be the quadrant 3. It's going to be quadrant 3 where both sine and cosine are negative. So if we were to add on 180 degrees or pi radians to this particular angle, we'll get to another location in quadrant 3 where the value for the tangent would be the same. So think of drawing a mirror image of this angle down here in this quadrant. Whatever this angle is, this is also going to be a solution to our equation. And the angle measure would be tangent inverse of 3, whatever that is, plus the amount that it takes to rotate around to where this location is. And exact in terms of radians means we would take tangent inverse of 3, and to that we would add pi radians. So pi plus tangent inverse of 3 will take us to another value that has that particular value for tangent. It's going to take us to another angle that's going to work for our equation. So one value for x is going to be inverse tangent of 3, and the other exact value is going to be pi plus the inverse tangent of 3. So those are going to be our exact values. And then we want degree approximations rounded to 1 decimal place. So let's approximate these, and then we'll talk about how you can kind of check and make sure that your work is correct here. So since we want degrees, you need to make sure you're in degree mode. So I'm going to change from my radians to degrees mode. And then we're taking the inverse tangent, which is right above tangent in blue, so second and tangent, inverse tangent of 3. And we're in degrees. So rounded to 1 decimal place, 71.6 degrees. And then we also want the degree approximation of this. Now I can use what I already have, but I'm not going to add pi, because remember, pi is in terms of radians. If I want to represent a half rotation in degrees, I need to add 180. So from the angle measure I have, I'm going to add 180 degrees, and that's going to take me to the other angle that solves my equation. So to 1 decimal place, that's 251.6 degrees. Now keep in mind 71.6, 251.6, those are rough approximations of the values that solve my equation. But just like any other equation, if I take my solutions and plug them back into the original equation, I should be able to show that the equation is true. So what happens if I take the tangent of 71.6 degrees? Well, I get almost 3, a little bit bigger than 3. Why did we end up with something that's bigger than 3? Well, if you look at those two degree measures, notice we had to round up. The 5 rounded up because it was followed by a 6. So that means the value of tangent also is a little higher than it really should be. but we're very, very close to 3, which is an indication that this would be a solution to our equation. Same thing if we do tangent of 251.6. Notice we get the same value, and again, that confirms that this does solve our equation. So be careful in terms of reading the terminology, understanding what you're being asked for. If we want an exact solution, well, tangent inverse of 3 is exact. This is an irrational number, so any other way of writing that, for instance like this, is really just going to be an approximation of this value. Same kind of thing over here. Pi is exact. We don't write 3.14, and tangent inverse of 3 is exact, so this is the exact angle measure, and this is an approximation of it. Okay, let's try another example. We want to solve cosine of x is equal to 0.6 on the interval from 0 to 2 pi. And again, we want to give the exact solutions in radians and approximations in degrees rounded to 1 decimal place. So cosine of x is equal to 0.6. In other words, 6/10 or 3/5. Well, that is not a number that I see represented on the unit circle. I know if we're talking about cosine, we would be looking for an x-coordinate on the unit circle. And this is not an x-coordinate that you can immediately read off, just looking at what's normally labeled. So the only way to isolate x in this case is to eliminate our cosine using the inverse cosine function. So if I apply my inverse cosine to both sides of the equation, then I can eliminate the cosine, I can isolate my x, and so we get x is equal to the inverse cosine of 0.6, whatever that happens to be. What quadrant would this angle be in? Remember, this represents an angle. It's the angle whose cosine is 0.6, but it's an angle within a specific interval. So when we talked about inverse cosine, it either corresponds to an angle in the first quadrant if the cosine is positive, or an angle in the second quadrant if our cosine is negative. So here our cosine is positive, which means we're talking about an angle in the first quadrant. So this is going to be the angle corresponding to the inverse cosine of 0.6. Now, as before, we've looked at equations involving cosine, and normally from 0 to 2 pi we have two solutions. This is one of them. What's the other one? Well, it's not necessarily going to be generated the way we generated the solution for tangent, because sine and cosine behave differently from tangent. Tangent values repeat after pi units, which is why we could rotate halfway and we ended up with another matching value for tangent. Cosine and sine don't work that way. What we have to think of now is what quadrant would we have to be in to find other values where cosine is positive. In other words, the x-coordinate at that radian measure is positive. Well, the other quadrant that has positive cosine values is going to be quadrant 4. So how would we generate the angle in quadrant 4 corresponding to a solution to this equation? Well, what do we know about angles if they have the same value for cosine? We're saying the cosine of one angle is 0.6, the cosine of the other angle is 0.6. What we know about those angles is that they would have to have the same reference angle. In other words, the angle we generate here in the fourth quadrant has to be related to this angle by the fact that this angle is its reference angle. In other words, it's going to be the angle that is the mirror image of this one if we were to rotate it down into the fourth quadrant. So it's going to be whatever angle we would get down here so that these two angle measures are the same right here. But the actual angle we want is going to have this angle measure, whatever that amount of rotation is. Well, what would that be if we're talking in radians specifically? Well, this angle right here is a full rotation minus this amount, minus just a little bit. So a full rotation in radians is represented by 2 pi, And 2 pi minus this amount, well, this amount, what is that? That's cosine inverse of 0.6. So this angle, our second solution, is going to be 2 pi minus cosine inverse of 0.6. That's going to be our other solution, the other exact value for a solution. So 2 pi minus inverse cosine of 0.6. And so if we want approximations, again, we're already in degree mode, we can just type that in. So inverse cosine of 0.6 should give us an angle in the first quadrant, and sure enough, it does. So to 1 decimal place, approximately 53.1 degrees. What about the next one? Well, 2 pi is in terms of radians, so if we're talking about degrees, 1 full rotation is 360 degrees. So 360 degrees minus this cosine value, so minus inverse cosine of 0.6. We plug that in, and the approximation is 306.9 degrees. So just like with the previous problem, we can check this. So if we sub these values back into our original equation, so cosine of 53.1, our first proposed solution, we get about 0.6. Again, a little bit more because we had to round in a particular way, but a little bit more close to 0.6. And then also the cosine of 306.9 degrees. Same value, also very, very close to 0.6. So that's pretty good confirmation that we've solved the problem correctly. So you'll notice we have a variety of different trig equations, and we have slightly different approaches to solve depending on the situation we're in. Again, the biggest focus is going to be using the unit circle. So identifying your trig values from the unit circle, finding the radian measures associated with those particular trig functions. It varies depending on the function we're looking at. The other thing that's unique about trig equations is the fact that our solutions repeat. So sine and cosine, secant and cosecant, those functions repeat after 2 pi radians, and then our tangent and cotangent repeat after pi radians. Of course, we've seen that that can be adjusted depending on what our equation looks like, but using this idea of what's happening on the unit circle from 0 to 2 pi, and then also this periodic nature of these functions is going to give us the information we need to solve trig equations.